Okay, so here we go. We're going to run the first simulation. I'll speed it up, but what we're going to do first is we're going to remove the snubber. So basically I'm going to, by putting the anode to ground, the diode is reverse biased, no current will flow, there'll be nothing being dissipated. So this is going to be looking at with no snubber. And what we're going to do is we're going to go to transient analysis. We'll set it up for 16.66 milliseconds. That'll give us one full cycle. So we'll see what this does. So if I say okay, so I said it takes a couple of minutes. So I'm going to speed up this video and we'll see what happens. Okay, so we're back. So here is the everything waveform, right? So this shows you everything, all combined. So what I'm going to do is, first thing I'm going to do is separate the curves, okay? So if we separate the curves, they get their own axes. So, okay, so this shows you everything over one cycle, but we want to zoom in a little bit now, right? So let's grab the very peak of the waveform. So we'll do this, right? So now we can see what's going on in each of the domains here. So looking at the eye drain, right? If I pull up a cursor here, okay, I can do the, see where it peaks out, okay, and basically what's happening is it's peaking out at 23.5 amps. Okay, so if we go to the right, what we can see is that with this 36 kilohertz, 17 microhenries, coming in with 50% duty cycle, okay, we should be getting around 24 amp. We go back now to this, okay, we can see that it's 23 and a half. So it's only 1 amp difference, right? Which is pretty good. And then if we look at what's going on here, right, we can zoom in even further. So here's your, so this is what we talked about, right? It ramps up and then it collapses and then you get the current in the secondary. And this is now running discontinuous before the next ramp. So this area here is discontinuous. So let's go ahead and we'll zoom in a little bit on just this part, right? Let's see if I can do this. Okay. And now what we want to do is we're going to just get rid of everything but V drain for now. Okay. So we'll get rid of this, we'll get rid of this, we'll get rid of this. We'll close that. And then we'll go ahead and we'll open this up. Okay. And then what I want to do is I want to just grab like this. Okay. So I want to show you now, this is the simulation with no snubber. All right. Now I also have a simulation or the actual unit where I measured this. Right. So if I come back and I go to here, okay. So I have no snubber, 230 volts AC. Okay, so this was measured on the oscilloscope, right? So if I try to put these up together, so look at what the simulation is saying, and look at what is really happening in the unit, right? I mean, this is pretty good for a simulation. This is pretty accurate about what we actually see. Right. The only difference is the levels, right? So this is saying that this is up at around 300 and let's see. Let's go back to, let's make that 0 so we can look at this, right? So this is 1, 2, 3, 4, 5. So this is 40 volts per, so we're about 360, maybe 380. This is about a 380 volt spike. Now, this is only 51, 52, 53, about 320, right? So we're actually getting a 320 volt. Again, this was with no snubber. And this is saying it's more like 380, right? So it's a little bit off, but you know, that's pretty good. I mean, look at how look at how this actual ringing is here. So this is the resonance with the leakage inductance, and this is the resonance with the leakage inductance, and then you come into the discontinuous mode where this is resonating with with the primary inductance and then the drain capacitance. So it says that it's modeled pretty well, right? That's really what this is saying. That this whole circuit is modeled well, right? This is really giving you an accurate picture. So if I were to turn on and put the snubber in now, so I'm going to say, okay, I want to try to bring down that peak, right? Because I have 400 volt FETs here, and that would be uncomfortably close. Assuming the situation, say I didn't know what it really was, and I had just simulated it for the first time, this would make me nervous. I would say I'm not happy with this. I want to get it down, you know, at least maybe half that, 200, 250, somewhere in that range, right, would be more comfortable than that close to the limit. So we'll go ahead and we'll run this again, and this time we're going to go ahead and I'll just speed it up again and we'll go for it. So we're going to run this again with the snubber in. All right. Okay, so you can see what's happened. This pretty much stayed the same, right? So this is still sitting here at about 134 volts. If I go back to what it was, and 134 volts. So it's the same waveform, it squashed this, okay? So you would say, oh wow, that's great. This is going to work perfectly. Well, not so fast, right? Because if you look at now, if I look at the actual data, okay, so now I'm going to look at, so this is with the snubber, okay? So what we can see, and if we just, I can just show you something here. So with the snubber, we're about 51, so 50, 100, 150, 200, 250, it's about 265. Without the snubber, we were 50, 100, 150, 200, 300, 350, we were like 370, 380. And as you can see, we're down to, we dropped to about here, right? So, but it's not down here. It's not cut off like it's showing in the simulation, right? There's still something there, but it's much less now, right? So why is that? Well, it's actually, the answer is pretty simple, right? If I go to what I have as far as like layout goes, right? So, okay, so if you look here, these are 400K resistors in parallel to give me my 25K, and here's the diode. So it comes, so this is good, right? So this is coming off the drain. The drains are here, and then it goes right to the transformer, and then the diode is right there. So that's a pretty low inductance road. But then you have these resistors that it goes through before coming back to plus, and this right here, I believe, is adding a slight little bit of inductance. Okay, so I know that if I were to go ahead and say our leakage is 350, let's say the inductance here, let's just say, for instance, the inductance in this path was, I don't know, 10% of whatever the leakage is, right? So that's pretty small, right? 35 nanohenries, right? That's a pretty small inductor, right? Let's see what happens now if I run it. What I'm going to do here is I'm going to stop it and do a preview so that you can see it. I'll wait till it hits 25% because when it hits 25%, I'll be at the 90-degree point. Okay, so I can go preview. I cancel this, right? And zoom in on this. Okay, and you can see that the spike is kind of back, right? It's not as high as it was, right? It's not as high as it was here. Here it was 380 volts, right? Now it's coming in somewhere around 210 volts. I mean, so that's why, right? That's why you're not getting, that's why you're not getting that, right? You're getting, it's really looking like this. So with with a pure snubber, it looks like that. But if you put a real world snubber in, so the way to overcome this now would be to say, okay, if this is true, which it is, because I can see it, right? Because I see what's going on. I can see what's going on in the real world with the snubber. I'm still getting this, right? And in fact, now it's 51, 52, 50. This is probably very close now to the same. So 35 nanohenries might be very, very close to what I actually have in series inductance, right? But I guess the point here is that if I wanted to drive that down more, I could just reduce this, right? So if I take this down to say 10K, okay, let me run that again. Right, I'll just run it. I go preview. We're going to cancel, and we'll just see what this is. Oh, okay, so let's grab this one. Right, so right around 220 volts. Right, it's getting much smaller. Right, so, and in fact, now let's view the snubber. Okay. So now if I say, let me look at this again, and I go like this. Okay, so here's the snubber voltage, right? Snubber voltage is at 107. It's at 101 and right now with the 25K. So here it's saying be 107, right? So 107 volts, and then you have 10K, right? So it's going to be 107 squared divided by 10,000. Is the power. It's going to be 1.1 watts. Right now it's about a half a watt. So it says I could definitely lower that resistance, you know, suck up another half watt and bring that spike down probably into the 200, at least another, drop at least another 20, 30, 40 volts from what it is now. But I'm not going to do that, right? Because it's still in a safe operating area right now, and I don't want to lose another half a watt, right? If I don't have to. Besides, this is just a breadboard anyway. But this is showing you, if you wanted to squeak and eke in every little ounce out of it, this would be the snubber. In general, snubbers are power wasters. But in this case, our leakage inductance is sitting at a fairly low, I mean, percentage-wise, it's only a couple of percent. Now, you can have, depending on how badly you wind the transformer, you can have, that could have easily been double this, right? And if you go to double this, trust me, these spikes go way up. They go way up. So this overall is a good design. So now if I grid tie, right? So if I grid tie, and then let me run this again. Okay, so we'll run the whole thing this time. This has really been good. So this is the whole thing now. But you can see that, you know, if we separate the curves again, you can see what's happening with current and with those peaks. So I wouldn't even have attempted this project if I wasn't able to simulate this. So I hope this has been helpful, and thanks for watching.